Hi, good morning. This is Charlie speaking. Let's go ahead and get started. And we'll put ourselves up here. Um, so there are a few people here. I appreciate that. If somebody can just go ahead and say hello in the comments, just so I know you can hear me. Looks like I'm broadcasting just fine, but I always want to be sure. Um, I don't know if this is going to take 2 or 3 hours, but basically, I like to go over in detail how the air conditioning system works and what sort of problems that we normally find with air conditioning systems, how to check for the wiring, and so forth. And Mark, thanks for doing that. I really appreciate it. All right. So let's go ahead and let's see what happens with this. Hi, Rosa. Thank you as well. All right. So I know nobody likes to do any sort of writing. I hope you guys have a little bit of a notepad or something with you. We are going to have to um, write down a few notes. All right. So a lot of the what happens with air conditioning, I guess, the main goal is we want to absorb the heat from inside the house, and then we want to move that heat to the outside of the house, and the result of that is going to end up being, the result of that is going to end up being we feel cool inside the house. All right. So how do we do that? We have to do a little bit of sciences. Believe it or not, the guy that invented air conditioning, I believe his last name is Carrier. So, obviously they named the air conditioning company after him. I believe his first name is Marcus. Marcus Carrier. Either that or it was a safety for the Bears. One of the two. But either way, we'll keep working. So heat does move. Heat is always moving from whatever the warmest object is to the coolest object. The bigger the separation between the temperatures, the faster the heat's going to move. All right. So if I am in a room of 75 degrees and I have a glass of ice water with me, the ice water is going to be 32 degrees. But that heat, that's 75 degrees in the room, is going to continuously be absorbed into the liquid. And until that liquid is completely a liquid, then that's also going to start raising in temperature until both temperatures are going to be the same. So either the liquid's going to end up being 75 degrees or so forth. Now, the second one is kind of an important, we talk about BTUs, and I do want you to be able to write that down real quick. I'll come back to this screen. Oh, Willis Carrier. Thank you, Mark. Sorry. So Marcus Carrier was the Bears player. So Willis Carrier is the inventor of air conditioning. Oops, that's okay. So let's. Oops, I did not want to do that. Okay. Sorry, guys. I'm having. There we go. All right. So let's start writing a few notes on here. All right. We do need to know the definition of BTU. That stands for British Thermal Unit. I guess I would have been better off going up and down on this one. But British. And the British Thermal Unit is the amount of energy, whether it be coal, gas, water, whatever it is, that's required to raise 1 pound of water (1 degree Fahrenheit). And I know I'm going to spell Fahrenheit wrong. Well, maybe not. 1 degree Fahrenheit. So I usually go through a little bit of a thing here where, let's see, I'm going to get me back on the screen here. There we go. All right. So I usually go through a little bit of a thing where how much energy are we needing when we start raising temperatures of water. And a lot of these questions I keep asking are, you know, if I had 1 pound of water sitting in front of me and I want to put that on a stove and put a fire on it, how much gas am I going to need to raise that temperature 50 degrees? All right. FAH. Mark, I'm going to stop liking you so real soon. But anyway, I hope you're giggling at that. So 1 pound of water, 1 degree Fahrenheit. If I have 50 degrees, or I have 1 pound of water that's 50 degrees, and I want to raise it and make it 100 degrees, I hope we're realizing I have to add 50 BTUs to that. And that's how long the fire has to burn and how much gas needs to be done. If I want to go from 100 degrees to 200 degrees and I still have that same 1 pound of water, then we're going to be using 100 degrees. Where it comes into play is on this second dot on here, where it says an object does not change temperature while it is changing state. However, it does continue to absorb or expel, it depends which way it's going, to absorb or expel BTUs. So as I have that 1 pound of water and it's sitting on the stove and it starts to boil, and when it's boiling, it's actually changing state. It's moving from a liquid to a gas state. As it's boiling, we know that water boils at atmospheric pressure. Water boils at 212 degrees. So while that water is boiling and as it continues to boil off, it's going to stay at 212 degrees until it's completely turned to steam. Now, of course, when it's turned to steam, it goes into the atmosphere, so we cannot control it any longer. But I want you to realize that as that's changing state, it's going to remain the same temperature. Same thing happens at liquids and solids. So if I take a glass of ice water, and I'm in a 75-degree room, then that 75 degrees is going to be absorbed into the ice water. The ice water will be 32 degrees. That's the freezing point of water. So as it keeps absorbing BTUs, then it's going to be melting all of that ice until the water is completely water and all the ice is gone. Once all the ice is gone, then the water will start increasing in temperature until it equalizes in the room. All right? But there's still an enormous amount of BTUs that come across. So when we tell people, 1 BTU is 1 pound of water, 1 degree Fahrenheit, but when we go from 210 to 214, that's not 4 BTUs. That's more like about 1,000 BTUs. All right. We can also raise the temperature. We can raise and lower the boiling temperatures of water. So I can keep water as a liquid if I increase the pressure to it. I could actually make water boil at extremely low temperatures. One of my favorite movies is Hunt for Red October. And there was a line in there when the Russian sub did their Crazy Ivan, and then the American sub put it in full reverse. And Jonesy, he was the sonar guy, or the guy that does all the listening to everything. He started yelling to captain and say, "Hey, we're cavitating." So cavitating basically is when you're boiling water under extremely low pressures, and then you move that water over to high pressure, and it collapses instantly, which is cavitation. So what they're doing is they got this submarine moving forward, and they throw it in reverse, and that thing is huge, and those propellers are extremely powerful. So they're creating such a negative pressure on the front side, or I should say the back side of those impellers, that the water actually starts to boil under those low pressures at that temperature. Once it passes over and gets to the high pressure side of the propeller, then those bubbles instantly collapse and it's just no good anymore. Or then it becomes a liquid. All right, so when we increase the pressure, we increase the boiling temperature. When we decrease the pressure, we end up decreasing the boiling temperatures as well, or changing from liquid to gas. Same thing when we pressurize an object, and that's not on our list. So whenever we pressurize an object, we're going to raise that boiling temperature. When we depressurize an object, we're going to decrease that boiling temperature. All of these items work with our air conditioning system. In a nutshell, they end up that's how the refrigerant works. So we're going to go ahead and we're going to bring a cold liquid inside the house. Remember, we have to absorb the heat. So if we bring a cold liquid inside the house and we blow warm air over it, we're going to absorb that heat. Heat travels from hot to cold. So if it's warmer inside the house than what it is in the liquid, then heat's going to move through the radiator coils into the refrigerant and convert that refrigerant from a liquid to a gas. And as it converts from a liquid to a gas, it has to absorb a tremendous amount of BTUs. And I need you to remember that part. It absorbs a tremendous amount of BTUs. And even on the other end, when we're discharging the heat, we're switching from a gas to a liquid. When we switch from a gas to a liquid, we're discharging a tremendous amount of BTUs. So in short, this is our typical air conditioning system. All right. I like you to realize there's about 4 different components. Not about, there are basically 4 different components that comes in here. So as we look at and let's start over here at the compressor. We'll start at the compressor. You can see that on the lower half side. So inside we have our furnace, our air handler. You can see our air conditioning coil on top. I know I put the blue flames on there. I'm sorry. I just thought they were cute, so I put them in there. But for the most part, the furnace isn't going to be running when the air conditioning is running. It kind of defeats the purpose. So we'll start at the compressor. In that compressor is going to have a gas. That compressor is going to compress the gas. Once we compress the gas, we're going to raise the temperature. Usually it goes up to somewhere around 150 degrees. If it's like, let's say it's really hot out and it's 100 degrees outside, the refrigerant's going to be 150 degrees. The outside air is going to be 100 degrees. So the heat is going to be transferring from the refrigerant to the outside air. So as we go through those coils that are up there, as we go through these coils that are up here, that is going to discharge the heat under high pressure. So that boiling point is up at the top, and it's going to convert to a liquid. It's still going to remain a high pressure, but it's going to end up being a liquid. So that liquid now is going to come back towards the house, and we're going to have something that's going to hold that pressure back, some sort of restricting valve that's going to be on there. When we restrict that liquid and only let a little bit in there, we significantly lower the pressure of that liquid. By lowering the pressure of that liquid, we're also lowering the temperature. So after we compress it, we're somewhere around 150 degrees. After we discharge heat, we're somewhere around 90 to 100 degrees. It's going to be warm to the touch, the liquid line. The liquid line goes through the restrictor. It's going to drop down to somewhere around 20 degrees. Probably not that close, more like 50 degrees. And then as we're 50 degrees or 20 to 50 in that ballpark, now we take that liquid, we blow it or blow warm air from the house over that. That's going to cause that liquid to boil because now our boiling temperature has been lowered because we lowered the pressure. It's going to convert to a gas. That gas is going to go back to the compressor and get compressed up again. And in short, that's how it works. But I think it's still a good idea to break down the air conditioning system and just get a clearer understanding. All right. So how do we get the heat basically from the room air or the outside air? how do we get it to the refrigerant? All right, so let me pop up a few slides here and we can talk about these things, and hopefully I won't go back up there. All right, so if we ever look at the outside coil, you can actually see these fins because they're just out in the open. They're very tight together. They're thin pieces of metal, and they're attached to the coils. And those coils run back and forth throughout everything, and the fins actually blow the air over. So big, wide, narrow pieces of metal where I'm going to flow air in between them, so they're able to absorb a tremendous amount of heat as the air passes through them, or discharge the heat as well. So it makes it pretty efficient. So that's how I'm absorbing the heat and getting it into the refrigerant. And the more times that coil passes over the more air, the more heat it can either absorb or discharge. So at this point in time, we're talking about warm air going over the coil. It ends up absorbing the heat into the coil, and then cool air is what we're going to feel coming through the house. The problem with these coils is because they're so close together, I should say these fins, they're so close together that if there's always going to be condensation forming on them. If we let dust get past the filter and get onto these coils, it starts creating a layer of mud. And once that layer of mud is created, especially with forced air furnaces that we have in the Chicagoland area, once that mud gets on there, we really don't have access to the top side of these fins to clean them. Or the bottom side of the fins, I misspoke, to go ahead and clean these things. So now we're going to have to hire somebody to basically remove the coil, get to the underside, and clean all these things just to let the air pass through. Because if the air cannot pass through, then there's no way to basically absorb the heat from the house and put it into the refrigerant. Everything is just going to stand by there. A key phrase I want you to be aware of, if you don't know, please write it down. It's called the latent heat of vaporization. We actually talked about it, or I talked about it already. That's the latent heat, is the process of absorbing or discharging significant amounts of heat when I'm changing state. So going back to the BTUs, we talked before about if I add heat to something, it changes from a liquid to a gas. If I discharge heat or remove heat from something, it changes from a gas to a liquid. All right. So the first one, going from a liquid to a gas, that's latent heat of vaporization. So we say it takes about 1,000 BTUs to take that 1 pound of water and completely convert it over to a gas. All right. The other term that's not written up here I want you to know is latent heat of condensation. All right. So latent heat of vaporization is the amount of BTU transfers when I go from a liquid to a gas. Latent heat of condensation is the amount of heat transfer going from a gas to a liquid. All right. It's a tremendous amount of heat that we can absorb or discharge, but I do need you to know when we're absorbing and when we're discharging. So for me, it was always easiest to remember that pot of water on the stove. All right. If I got a fire underneath that stove, fire underneath the water, that water is absorbing heat. All right. As I'm absorbing heat, I'm changing from a liquid to a gas. And then vice versa. If I'm removing the heat, I'm going from a gas to a liquid. Latent heat of vaporization and latent heat of condensation. All right. So the evaporator coil, and we really give two names in air conditioning. We have a condensing coil and an evaporator coil. And if you think about what I just talked about, when we're evaporating, we're changing from a liquid to a gas. And when we're condensating, we're changing from a gas to a liquid. So refrigerant enters at about 20 degrees Fahrenheit. I think that was the first number I threw out there. We're going to assume that the house is somewhere around 75 degrees. And this is a simple test we can do as well. All right. It's going to change from a liquid to a gas. And as it changes, it's going to absorb the heat in the air that is blowing over the coils where it comes through it. So it comes in as a liquid at 20 degrees, absorbs heat from the house, and then the refrigerant is going to end up leaving as a gas roughly about 50 degrees. Now, when we go back and showing the lines again, we didn't really talk about the line set, but if you look at your air conditioning system, you're going to see two tubes out there. We call that the line set. One is going to be skinny and one is going to be fat, or bigger for a lesser word. The bigger line is also known as our gas line or our suction line or our low pressure line. That one's going to be cold to the touch. So, we're saying it's going to be around 50 degrees when we touch it. So if our hand is on it and we feel it, it's actually going to be pretty cool. Where it's a liquid coming in here is going to be after the restricting device. So that's going to lower the temperature down to 20 degrees. That's not going to be an area that we can actually touch. All right, so that's going to be inside the plenum or the air conditioning coil. Typically it's going to be the capillary tubes, but we'll get to that in a little bit. All right. So let's go back here one more time. I want to pop those words back up there again. And make sure we got everything on here covered. So warm house air boils the cold liquid. We chatted on that. Large amount of heat is absorbed. That's a test question. I need you to be aware of that. The heat that's being absorbed is called latent heat. And we're going to refer to this process as latent heat of vaporization. When we're discharging the heat, as we're changing state, that's a latent heat of condensation. And again, it does make for a very efficient heat transfer. So we have our indoor coil. We were just talking about that. We left the indoor coil as a gas and it's 50 degrees. We said heat travels from hot to cold. So we need, if it's 100 degrees outside and my refrigerant is 50 degrees, well, the outside air is still going to the outside air is still going to be putting heat into the refrigerant. So I need to do something with that gas refrigerant to go ahead and increase the temperature of that. We mentioned earlier in our science stuff that when we increase the pressure, we're also increasing the temperature as we come to it. So this is just an old piston-shaped pump on here. Right now we use squirrel compressors to go ahead and put the system in there. But if it comes in as a gas, and the only thing that can go through these air compressors is a gas, and we're going to hit that with the temperatures that we check air conditioning in a little bit. So we can only send gas through the air compressor. It comes in at 50 degrees, but then once I pressurize the system, it's going to leave at about 150 degrees. All right, so just by pressurizing that gas, we increase the temperature by 100 degrees. Now it's warmer than what it is outside, and this air compressor is located in the outside compressor cabinet or condensing cabinet. It has a couple different names, but it's really the same thing. So the air compressor is in the outside metal cabinet. All right? And as it leaves there, it's 150 degrees. When it's 150 degrees, it's warmer than the outside air. So as we run it through all the coils and the same fins that are outside, we're going to actually start discharging heat to the outdoors. So as we discharge the heat, all right, come in at 150. Here we're saying it's 85. Outside air is going to probably go up about 15 degrees. And I did leave that off indoors. I want you to remember that air conditioning systems typically have a 15 to 20 degree temperature drop. And that's a real simple, easy test that we could do to see if these things are basically doing what they're supposed to be doing. We turn the air conditioning on. If it's 70 degrees in the house, we should be expecting it to be 50 to 55 degrees on the other side of the air conditioning coil in the plenum. Anything that's higher than that or lower than that could be an issue. High pressure liquid, because we raised the boiling point, and it leaves there at 100 degrees. So the skinny line is going to be warm to the touch, and then the suction line, before it goes into the cabinet, remember that 150 degrees is directly after the compressor. Before the compressor, it's 50 degrees. So what I'm going to be able to feel is the suction line on the outside that's 50 degrees, and the liquid line on the outside was typically 100 degrees. All right. Forces hot, high pressure refrigerant to the top of the coil located outside. The refrigerant travels through the coils. Same air transfer is happening, but in this case, we're discharging heat. As I'm discharging, I'm condensing my refrigerant, changing from a gas to a liquid. And again, as I change from a gas to a liquid, I discharge, or I release, a tremendous amount of heat that I had inside the refrigerant. All right. This is called latent heat of condensation when this happens. And we're just talking about the heat transfer without the temperature change. That is latent heat. So we started our indoor coil again. We absorbed heat. We're a gas. We send the gas to the compressor. We compress it. Now we make it a high temperature, high pressure gas. We blow outside air over it. We get rid of that heat. On there, it changes back to a liquid. It's still high pressure, but now I need to lower that pressure, because when I lower that pressure, then I'm going to go ahead and lower the temperature as well, so I could bring a nice cold liquid into my indoor air. All right. So the capillary tubes, and I'll show a picture of that in a little bit. The capillary tubes are going to be our typical bottleneck, our typical restricting device or metering device. All right. There are other ones out there. There are mechanical devices, and they call TXVs, or thermal expansion valves, and I'll show you what those look like and how they work in a little bit. But for now, I want to focus on the science behind the air conditioning. So what we're doing is we're holding that pressure back, and as we hold that pressure back, we're going to have that 100-degree temperature. And then as we let a little bit of the refrigerant out, so we lower the pressure of it, that significantly drops the temperature as well. And as we drop that temperature, we're going to drop, that's what we're going to be sending into the air conditioning unit. So now we have a 20-degree liquid, and we're going to bring that liquid to the inside. What we're looking at here is a schematic of a typical A coil. So basically, you'll see how I have two slabs leaning up next to each other, and then there's those little bit of coils that keep going round and round. That skinny tube is basically what's holding our pressure back and only letting a little bit of refrigerant come through at a time. And these systems are all engineered to work together. So the outside cabinet and the size of the compressor and the size of the coils have to match the indoor refrigerant coils as well. They can't be like a 4-ton unit outside and a 2-ton unit inside. They must match. Otherwise, they're not going to work properly. So if we ever get inside, and sometimes you'll see a panel on the indoor coils, so you could pull that panel off. Sometimes you can see it when you remove the humidifier, and you can look for these coils. Typically, we don't find too much going on with them. But if they're leaking, and you'll see that with signs of oil, but we wouldn't get our temperature changes anyway, or dented or damaged in any way, we should photograph them and document that as well. Here's an actual A coil that comes in there. So you can see how the skinny line, we call that the refrigerant line, and then that goes into those capillary tubes again. So the spinning of the capillary tubes that's on there, that's what's going to hold everything back. And you could see the fins. I like this picture a lot because we can actually see the coils and how they're going back and forth on there. We can see the fins, how they tighten and keep the air coming through it as well. And then when it leaves through the thicker line up there. That's called the suction line. So it comes in as a liquid and leaves it a gas as we absorb all the heat that's inside the house and put it into the refrigerant. So now we're under low pressure. We're a liquid. And this much right here with this drawing, I am expecting you to be able to write this down or draw this down. I want you to know there's 4 main components of an air conditioning system. All right. We're going to have our indoor coils and our outdoor coils. We're going to have a compressor, so something to increase the pressure, and then something, whether it's the capillary tubes or TXV, for a generic term, we're going to call it an expansion device, all right? So we're going to have something that's going to lower the pressure, or a metering device. I like that as more of a generic term as well. You're expected to know, when is it the high pressure side, when is it the low pressure side. So as we're looking at the drawing and we start at the top, anything after the compressor all the way up to where it says the expansion device, in between, on the right side of that, that's all under high pressure. Everything on the left side of that is all under low pressure. And then if I took another imaginary line and I put it across the coils, you're expected to know when it's a gas and when it's a liquid. So from the indoor coil, as it leaves the indoor coil, goes through the compressor and enters the outdoor coil, that's all a gas. And then from the outdoor coil, as it leaves that coil, including the expansion device or the metering device, until it gets into the indoor coil, that's where it's all going to be a liquid. The only places that we're supposed to be changing state is going to be in those coils. All right. So I'm expecting you to know when it's high pressure gas, when it's high temperature gas, when it's high pressure liquid, when it's medium temperature high pressure liquid, and then after the expansion valve, we're going to be low temperature, low pressure liquid. As we go through the coil and we change to a gas, we're going to be medium temperature, low pressure, and as a gas. Hit our compressor again, high temperature, high pressure, still a gas, change state in the outdoor coil back to a liquid. All right. And this is the same thing of the drawing that we saw in the beginning. And again, let's just start at the compressor. All right. We're a gas when we come in there, and we're going to pressurize that gas. As we pressurize it, we're going to be high pressure, high temperature gas. I think what I'm going to do is take this particular slide, because I like it so much. It kind of breaks everything down to, when is it a gas, when is it a liquid. As we look at the drawing, any of those lines that are thicker, those are going to be gas lines. Any of the lines that are skinny, those are going to be liquid lines. So the compressor, we come out of there, it's high temperature, high pressure, and it's a gas. It goes through our coils. We discharge the heat, we convert to a liquid. We're still high pressure. Our temperature is dropped, so we're medium temperature, and we're a liquid, so roughly about 100 degrees. As we go through our metering device, we're going to drop our pressure. When we drop our pressure, we drop our temperature. And that's going to also be a liquid. It's going to remain a liquid. So low temperature, low pressure, liquid, roughly about 20 degrees. We're going to pass it through our indoor coil. We're going to absorb heat from the inside. As we're absorbing heat, we're going to change from a liquid to a gas. So we're going to go ahead and expel gas from the coil. It goes in as a liquid, comes out as a gas. So as it comes out as a gas, it's going to be still low pressure. It is going to be a gas, and it's going to be roughly that medium temperature again. So low pressure, here it's saying low temperature, but roughly 50 degrees, and it's still going to be a gas. We go into our compressor, we pressurize it, we heat it up again, and the cycle keeps going on and on. If you look at this kind of carefully, you'll see that that compressor, and I'm not talking about the fans that go ahead and blow the air over the coils, the compressor is really the only moving part of the air conditioner. So as I'm adding pressure into the system, I'm also releasing pressure at that metering device. And those things are supposed to be in tune perfectly. So when the system is fully up and running, as I continuously add pressure to the system, the metering device is continuously releasing the same amount of refrigerant so that I could get that equilibrium of pressures, and I can go ahead and make that I'm forgetting my word here, going from a liquid to a gas or gas to a liquid. My change of state is what I was looking for. All right, we kind of talked about this on some of our field trainings, and I just want to go a little bit more about some of the terms and things that we use. The first one is the term ton. Whenever we deal with air conditioning systems, we call them a 1 ton unit or a 2 ton unit or 2.5 tons, wherever it comes in there, but the term ton. I'd like you to know where it came from. This is kind of a test question that I've heard of as well, so I'd like you to be aware of it. 12,000 BTUs equals 1 ton, for air conditioning. And how they determine that is if they had 1 ton of solid ice, it takes 12,000 BTUs to convert that 1 ton of ice into a liquid. So again, we're changing state, going from a solid to a liquid this time, and it takes 12,000 BTUs to go ahead and melt 1 ton of ice. Hence the term ton. So when we look at house systems, we kind of want to get a rough idea if the system is acceptable or not, or if it's too big or too small when it comes with it. The term that the HVAC contractors are going to use is something called a J calculation. And at that point in time, they're going to be using the location of the home, and they talk about how many heat days we have. They're going to look at the amount of insulation, the square footage of the home, how many windows there are. Basically, what they're going to try and determine is how much heat loss is going to be happening in this house so that they could go ahead and put the right size systems to go ahead and replace that heat loss or heat gain. When we're talking about air conditioning, the houses are going to gain heat. We need to absorb that heat and remove it from the house. All right. So this is just a rule of thumb. This isn't something to hang your hat on or a hill to die on at all. It's just a rule of thumb. In our area, and I would say it's more to about 1,000 square feet per ton, that's a pretty decent rule of thumb. The more efficient a home is, the smaller the air conditioning we need to be. Nowadays, we're putting all this foam and everything else into the houses. We really don't need that big of air conditioning systems because we're not going to have as much heat getting through that foam and heating up the house, so we don't have to remove the heat as fast as when the older homes had very little insulation, drafty windows. All that heat gain was coming into the house, and we just had to remove a lot more heat, so we needed bigger air conditioning systems. All right. So a decent rule of thumb is about 1 ton for every 1,000 square feet. You really don't see too many systems smaller than 2 or 2.5 tons. Most of the ones we're going to run into, the smaller homes, are going to be about 2.5 tons. In my house, I do not have a big home. We have a 2-zone system, so they don't really run all that much. It's roughly about 1,500 square feet. And I have 2 separate zones, and they're both 2.5 tons. So we don't divide everything up when we're doing it and saying, well, wait a minute, you got 5 tons now for a 1,500 square foot home. What I do know is that for the most part, my second floor air conditioning and heating system is going to be running in the summertime more. Heat is going to rise. I have an open staircase. So that's the one that's going to be doing most of the work. The first floor one would hardly run at all. But it did. If the heat does come in there, it does actually run. All right. What we don't want to see, though, is big air conditioning systems on small homes. Because when the bigger the air conditioning systems, they're able to remove heat extremely fast. Now, just getting rid of the heat doesn't always make us comfortable. All right. If it's hot and wet or humid, that's actually uncomfortable. I should say cold and humid is uncomfortable. All right, it gets to be clammy. So when air conditioning systems are also running, they're going to also be removing the humidity that's in the air as well, so we can make it cool and dry. The ultimate goal of an air conditioning system, when it's properly sized, is that the air conditioning system should pretty much run 24 hours a day on those temperatures at around 100 to 110 degrees in our area. And as it's running, it's constantly removing the heat that's coming in there. It's constantly removing the humidity that's coming into the house. It's giving you a comfortable, cool, and dry. Now, that doesn't mean that it won't shut off here and there, but for the most part, it's going to turn on and stay on. Going back to my house, when I have a 2-zone system, my upper floor one in the hottest days of the year, that should be running pretty much consistently. And then rarely should the the first floor go ahead and kick on. So the problem with large air conditioning systems is A, they cycle on and off very quickly, and that shortens the lifespan. So the more they turn on and off, the shorter the lifespan is going to be on these things. And the second problem is going to be that they'll remove the heat extremely fast, but they don't remove the humidity, so we're left with cool and clammy air inside the house. This here is a common test that you could do, those simple turkey thermometers or a dial thermometer. They work tremendously, all right? So we're looking, and I want you to remember these numbers, 15 to 20 degrees. That's our typical temperature drop. I normally don't take temperature readings on the filter side of the fan. I kind of just look at the thermostat when I lower the thermostat to see what the temperature is, because that's the same temperature of the air that's going to be coming through it. But I do take the temperature above the plenum up there, and I'll usually either remove the humidifier and get access to that area. I'll look for gaps in the ductwork itself that comes in there, and if I can't, I'll find the closest radiator. For those of you that decide that you're going to want to work with the thermal imaging camera, they're actually pretty cool. You just walk right by the registers, and you can go ahead and get a reading of whatever the temperature is that's coming out of there. What you don't want to do with those things is shine it on the ductwork and take your temperature reading that way. The ductwork is never going to be the same temperature as whatever the airflow is, all right? So you want to get the temperature of the airflow, and that's where those turkey thermometers just make life a lot easier. So we're looking for it to be somewhere around 50 to 55 degrees. Supply temperature is typically 55 to 60. It's saying that temperature because it's using the return as saying that that's 75 degrees. But I find that most people keep it somewhere around 70 degrees. So whatever temperature it is coming in, we're looking for 15 to 20 degrees of a drop going out. Testing air conditioners. This is a big one. All right. Most home inspectors will use the temperature is 65 degrees. And I'll be honest with you, a lot of air conditioning systems can go all the way down to 50 degrees and they'll run just fine. All right. We'll talk about heat pumps and what's the difference between an air conditioning system and a heat pump in a little bit. But heat pumps can run all the way down to 35 degrees, and they'll be able to work just fine, all right? But for us, being cautious, we're going to use the temperature of 65 degrees, and we kind of stick to that if it's been that temperature within the last 24 hours, all right? Now, the reasoning why we don't want to test air conditioners at a lower temperature, I need you to go back to your memories a little bit when I showed that compressor out there earlier. An air compressor can only compress air. All right. If I try to push liquid through that air compressor, then I'm going to damage that air compressor, plain and simple. So you might go to a house, you're inspecting the home, and then you look at the air conditioner, and it might be just fine. But you turn that air conditioner on and the refrigerant inside that compressor or around that compressor is a liquid. Now you're going to be pushing that liquid through the compressor, and that's just going to damage the scroll coils and everything else. So we don't want to take that chance. We don't want to damage the compressor whatsoever. It's a common practice that we do. So I'm going to ask that you don't test air conditioners. And whatever number you want to choose is up to you. We're going to throw out a very conservative, safe number of 65 degrees. So like this time of year, and not until April probably, will we be testing air conditioners again. So, and we just have a standard disclaimer in our form. So determining the size of the compressor, even though this isn't a real data plate that's up there, it was a real data plate. And what I did was I tried to pull all the numbers and everything else that's on there so we could do a little bit of decoding. All right. I know in the field, I usually tell people to look up buildingcenter.org. And I'm going to actually type that in the comments here. So you got it. So, and I'm pretty sure this is the right website. Buildingcenter.org. All right. And that's up there. So when you go there, what they did was they took every manufacturer and even the different years that the manufacturers did it, and they were able to decode all the different data plates that are on there. All right. But there's some things that you're going to have to kind of know so you can figure everything out. So in the model numbers, that's usually where they're going to hide the BTUs. And I shouldn't use the word hide, but that's where we're going to find how many BTUs this unit's going to be there. So you look for multiples of 12s or even 6s, because 6 is a half of a 12. So that would be a half ton. So if we go at the model number on this one, and I'm seeing TTX030. All right. So the 030 is going to basically tell me 30,000 BTUs. So at 30,000 BTUs, 12 times 2 is 24. 24 plus 6, which is a half a ton, gives me 30. So 2.5 tons is the size of this air conditioning unit. All right. Now, since we got the data plate up here, I'd like to go over a few other pieces of information that we can get out of this. All right. Now, I believe this is a Train, the XL1200. That's a Train model out there. And they've been actually very good about typing the manufacturer's date in the upper right-hand corner of these data plates. So this one right here was manufactured August of 94. So that part's easy when we come through it. But if you go to that buildingcenter.org and you look up that data plate on there, or I should say that serial number, the J32210593, you know, and that I do, if I remember right, there was an actual serial number on there. It should show you how to decode that and come up with August of 94. But in this case, it was easy. All right. The next thing I want you to look for is the maximum breaker. Sometimes that's listed as maximum fuse that's on there. Now, in our company, we always take a photo of the data plate. All right. This is a big deal to us. We take a photo of the data plate, and when we go inside the electrical panel, now we have a reference that we can go back to. But where it says maximum fuse on there, that's the maximum fuse. We don't want to find one smaller than that either. All right. We should actually try to be somewhere as close as we can to that fuse without going over. So here they give you a recommended fuse or recommended breaker as well. And that's also 25 amps that's written on there. The HCFC 22, that they're talking about the refrigerant on there. The next number I want you to look at is that minimum ampacity. The minimum circuit ampacity is talking about the wire size, basically. So when this unit is running, I need to be able to allow 17 amps to flow through this system. So if I start doing my wire gauge measurements again, and what I should have committed to my memory, I know that a 14 gauge wire is only good for 15 amps. Well, this is telling me I need at least 17 amps. So that 14 gauge wire isn't going to cut the mustard. All right. The next size larger wire is going to be a 12 gauge wire. That 12 gauge wire is good for 20 amps. Okay, 20 amps is more than what this thing needs for its minimum amp. So I could put a 12 gauge wire and feed this air compressor unit or compressor cabinet unit. I could feed that with a 12 gauge wire. Then it says that the maximum fuse I could put on here is a 25 amp breaker. So even though a 12 gauge wire shouldn't have bigger than a 20 amp breaker, the manufacturer of this air conditioner is saying it's okay. And as long as the manufacturer says it's okay, it's okay. So in this situation, we could put a 12 gauge wire on a 25 amp breaker. That's not a problem. And if they want to go with a 10 gauge wire, they could do that too. You know, it's a little more expensive. It doesn't matter. You know, it's safer. But by all means, when the manufacturer of the air conditioner said this is the minimum, this is the cheapest you could go, and it still make it safe, well, then it's still considered safe in their eyes. All right, so off of this data plate, we know our maximum breaker. We know the wire size that it should be. We know how big our system is, and we're able to determine how old our system is too. All right, overfusing is okay. That's kind of what I was talking about beforehand. Not always are we going to be able to see the data plate, all right? Now, this rule of thumb is strictly that, just a rule of thumb when we come to this. And I'm going to go ahead. And clean up my board again. Let's go ahead and make that cheap little chart when I come to it. I gotta get a better eraser on my whiteboard. Alright. So basically, I like to have a little chart. I would strongly recommend that you get something like this so you can memorize these things. So if we write up on the left, amps. Let's find another one. And then we'll have copper. And then aluminum. And this little chart is actually something you should have with you all the time. Every time we look at an electrical panel, this is what we're going to end up with anyway. So for amperage, we're going to start with 15, 20, 30, we'll jump up to 50, 60, 100, 200. And then we draw some lines through all this. All right, so for a 15 amp, I'm going to need a 14 gauge copper wire or a number 12 aluminum. For 20 amps, I'm going to need a 12 or a 10. 30, I'm going to need a 10 or an 8. 50, I'm going to need an 8 or a 6. 6, 4, and then the NEC does say 4 for 100 amps. But I always like people to know number 3 in Chicago. All right. And it's typically a number 3 copper that we're going to run for there. Number 2 aluminum is a very common service drop in our area. And then the next one, you know, if you see a pattern, 14, 12, 12, 10, 10, 8, 8, 6, 6, 4, makes it for an easy way to remember this stuff. But for the next one, we're going to transpose these. And then, so we're going to go 2/0. And 4/0 if it was aluminum. So that's talking about a 2-aught wire and a 4-aught wire. So when we're dealing with the overfusing, and this again is all rule of thumb, that data plate that we saw before, that's our priority. This is not when it comes to it. All right. So let's say that I was feeding that air conditioning unit and I didn't have access to the data plate at all. So I'm feeding that air conditioner with a 10 gauge wire. What I'm going to do is take the next larger size wire, which is a number 8. Whatever breaker can protect that, that's what I can go ahead and use. So I'm going to go back to the slide drawing in a second, and that's at 125%. But if I had a number 10 copper wire on a 15 amp, or I'm sorry, on a 50 amp breaker to go ahead and protect everything. And let's see if I get back there. Good. So we got a 10 gauge wire coming across there. You can see our little fuses are marked at 50 amps. And that's part of that overcurrent. Now the reason they allow this is when the air conditioners start up, they use a lot of electricity. All right, there's that sudden surge of power that's going to come into this. And as that starts up, we don't want the breakers to trip because it's over. Now they're dedicated, nothing else is supposed to be attached to this. So it's just going to be the air conditioning. If that air compressor seizes up and it's not working right anymore, then it's going to be using a lot more than the 50 amps, and it's going to go ahead and blow the fuse anyway. All right. So with air conditioning, I'm talking about central air conditioning systems. This is not acceptable for through wall units or window units or anything other than a central air conditioning compressor cabinet on the outside. And the overfusing is actually normal, and the reason is because of the sudden start. All right. This is just a little bit above and beyond what most home inspectors do, but I actually kind of like it a little bit. Let's see if I go back a couple slides. And we go back to this data plate here. Something that I didn't talk about was the rated load amps. So if you look at the bottom of that chart, you can see the compressor motor has rated load amps of 12 amps. The FLA stands for full load amps. Sometimes you'll see LRA, and that stands for locked rotor amps. All right. So full load amps is usually going to be the charge or the startup power that it's going to use. So this data plate is telling me when it starts up, it should be somewhere around 17.5 amps. After it's running, it should be running at somewhere around 12 amps. I take that plus the fan motor RLA, that gives me 13. So if you're going to go a little bit overboard, and I like to do this, all right, so if you're going to go a little bit overboard, we put amp meters on the power lines that comes through there when the air conditioner is running, and it should be somewhere between 60 and 90% of whatever the total of the RLA is, or the rated load amps. Now for me, I know this is wrong, but it's just a nice, easy way for me to remember it. When I see the RLA, I like to think of it as running load amps. So after the system is running, these are the amperes that I'm supposed to be there. Now, I'm not supposed to be at max of that. If I get up that high, then my air compressor is struggling, and that usually indicates that I'm getting to the end of its lifespan. So I should be under 90% of whatever the total RLA is. So this time we had 13. So remove 1.3 out of that. So we'll go back down to 11, 11 and a half, somewhere in that ballpark. I should be below that. If I'm over 12, then I'm going to start questioning things. And we could go ahead and just simply put that amp meter right around the wire, and then that's going to be able to read the current flow going through that wire. And let me just be clear. Very few people ever go that extent. There's always simple steps that you could do with air conditioners, and there's even more. Testo makes a great temperature reading system. So as we're looking at the condenser unit or the compressor cabinet, again, it's the same thing, just different words. On the bottom there, we see the refrigerant line connections, so the thicker line and the heated line. We can actually put thermostats on those, and we can go ahead and figure out what the temperature difference is, or the delta on that, and that'll also tell us if the air conditioning system is working properly. But truthfully, and we don't do that, all right? I was toying with the idea of doing it, but we don't. And we get enough accuracy that everything's working fine just by checking the temperature drop on the inside. Now, I'll put my hand over the top of this coil and make sure I got warm air coming out of it. But again, that's just a rule of thumb, all right? So that air coming out of there should be probably somewhere around 15 degrees over the ambient air temperature. So whatever it is, it's going to feel warm to my touch, all right? On the suction line, because we said the suction line is cold, all right, and it's going to be warm or hot and humid outside, so condensation will form on that. Sometimes there's a there's insulation that's wrapped around that pipe as well, and that insulation gets deteriorated with the ultraviolet rays of the sun. So the whole purpose of that is to prevent the condensation, or I should say the whole purpose of the insulation is to prevent the condensation. But, if it's outside and it's just condensating and it's dripping on the ground, I don't really see that as a problem, and I don't really make a comment on it. All right. However, if I'm losing refrigerant and I don't have enough in the system, then that pipe is already going to be much colder than the 50 degrees. It's going to be below freezing. When it gets below freezing, any condensation that forms on that pipe is going to freeze with it. And then you end up seeing this big ball of ice on the suction line. That's a pretty strong indicator that we're low on refrigerant. And usually if you're going to have it there, you're going to also have ice forming on your indoor coil as well. Now, it's not always 100% true. All right. So we always want to do our best to see what we could see. But ice on an air conditioning system is not a good thing. That usually indicates low refrigerant. All right. I like to feel that the liquid line is warm and that the suction line is cool. And just do that on pretty much every unit when it's running. So I know there's test questions about compressor cabinets being level. All right. In all reality, yeah, they should be level. I really don't make a big deal when they're not. This side is telling us we can go all the way up to 10 degrees, and it's not going to be that much of a big deal. But, if it was a piston compressor, and the whole purpose for this levelness is that the motors that are spinning, they need to have oil to go ahead and keep them lubricated. And if they're not lubricated, or the oil's not getting to them, then the motors are going to seize, and then obviously the air conditioner is going to be damaged. And the compressor is the most important part because it's the only moving part, so it's also the most expensive part, and that's the one that we want to protect, all right? So keeping it level is a good thing. However, air conditioning systems today are dealing with scroll compressors, and they don't have a tray of oil underneath them to keep them lubricated. The oil and the lubrication that they're using is actually inside the refrigerant itself. So as long as that refrigerant is moving freely, then everything's going to stay lubricated. So I don't make a big deal with it. But then if we start looking at the cost to cure, how much does it take to put a little bit of stones or another rock or a leveling pad or something underneath that to go ahead and make it level again? It's effort, it's work, but it's really not that difficult. So just do it and be safe. And to me, it's not that big of a deal, but I'm still going to document it. Disconnects on the outside are a big deal to me. There's parts of our state, I know when we were doing field training out in Illinois Valley Community College, so that was in the LaSalle, Peru area, we would use homes out there to do the field training. And it was to my amazement that they didn't really have any exterior disconnect. So that's kind of a local jurisdiction on what they're going to enforce or not enforce. At first, the first house we looked at, we come up to it, and I'm calling it out as a defect, and I'm kind of perplexed. And then I looked at all the other houses in the neighborhood, and none of them had it. So that's why I can only assume that whatever the reason is, they're allowing it. So the purpose of this disconnect, all right, it's there to design or to protect the guy that's working on the air conditioning cabinet. If he goes in there, he opens it up, all of a sudden it starts working. He needs to be able to turn that power off right away and get it there. So for me, when I look at these disconnects, if I'm in front of the unit on my knees working, I like to see a disconnect that's within easy reach, just in case the unit does start up. It's a good idea to check those connections at both ends. If they're metal, liquid tight, flexible conduit, then we can use the conduit as our grounding system. If the connections are plastic, then we're going to need a separate ground wire that come through it, so that we can make sure if there's any, we can make sure that the breaker will trip should we get a ground fault on the in the cabinet anywhere. All right. So I like to check those connections and make sure that they're nice and tight and secure. And if they're loose, we got a paragraph for that too that we'll put in the report. Warm air discharges near the compressor can most likely reduce the capacity efficiency. All right. So sidewall furnaces, sidewall water heater discharges, and dryer vents. Now the furnace, sidewall furnace discharges, I mean, the furnace and the air conditioner are not going to be running at the same time, all right? And if they are, they might be two separate units. So because of efficiency, I can't buy into that one. However, the condensation that comes off of a sidewall vented furnace, because it is a condensing furnace, that condensation is very caustic. And if that gets blown onto the fins on a regular basis in the winter, we're going to start rotting and deteriorating those fins like there's no tomorrow. All right, so that in itself, I think, is a big deal. And yeah, the air shouldn't be blowing on the fins. It should be off to the side somewhere. Water heater discharges or sidewall water heater discharges. Now that will operate when the air conditioning is operating. And we're trying to, remember, we're trying to discharge heat. So if we have hot air that's blowing on top of it, that just makes it more difficult to go ahead and discharge the heat. And direct vent water heaters are also considered condensing water heaters. Condensation does come out of that as well. So yeah, I think that's going to damage it also. And dryer vents, I mean, let's think about it. We got wet clothes that we're trying to dry, so we're exhausting humidity, plus the heat, so that could actually damage them as well. So all these air conditioning compressors and the coils that are around it, we want to make sure that we have good airflow, and then we want to make sure that whatever air flowing across them isn't going to be something that will damage the units themselves, all right? Such as the furnace, the water heater, and the dryer vents, all right? So for the most part, the fans are going to blow the air upwards, so the outside air is going to come through the coils, and then it's going to be blown upwards. All right. They can also rotate vertically and diagonally depending on the manufacturer. That's true. You should hear a hum. You should hear a minimal vibration coming out of it, but it shouldn't be loud. It shouldn't be rattling. It shouldn't be shaking. Those are all things that could tell us that we got some bad bearings or something that's getting to the end of its lifespan. It should be covered in the winter. That's according to the experts. I'll be honest with you. I never cover my air conditioner, and I don't see where there's any real damage that comes to it. And if you disagree with me, I respect that, So I do run into them a lot when they are covered. For me, it's just a pain in the butt, because I need to pull that cover up to get to the data plate and take pictures of it and check to make sure my conduit is secured. And then I need to lift it up high enough to look at my fins and see if they're damaged in any which way and take a picture of those. All right. Same thing with the blower fan on top. This should be moving a lot of air so we can get that air flowing across the coil. No squeaks, no sounds, nothing else like that. I see this every now and then. Somebody will put an air conditioning coil under a deck. And again, it's only really a problem if you think that the airflow is being limited. For a rule of thumb, they tell us 4 to 6 feet vertical clearance. I don't know if I could buy into that 100%. I think it would work just fine. But when you're talking about only 6 inches to a foot, yeah, that could probably restrict the airflow. Same thing on the sides, all right? When we have bushes around the outside of these things, or it's pushed up against the wall of the house, then the air will flow through the other parts of the coil, but it won't flow through that part of the coil. So we reduce a lot of efficiency. We need the more air that we run through, the more amount of coils, the more efficient a unit is going to be operating. All right. The indoor coil, some people refer to that as the A coil. It only gets its name because of the shape that it's in right now. So because it's up and down like the letter A, That's the only reason why we call it an A coil. The true name, and the name I want you to remember, is going to be evaporator coil. And mainly because this is where we're converting again from a liquid to a gas. So we're vaporizing, so we're going to call this the evaporator coil. All right. The furnace serves as the fan. So the outside condensing cabinet, where it converts from a gas to a liquid, we have a special fan strictly for that cabinet outside. Inside, however, we use the same circulation fan that we use to make heat in that house. So that's our blower fan coming across. Colder air is harder to push. That's a true statement on there. So most of the modern furnaces, they're going to have multi-speed fans on them. Sometimes 2 speeds, sometimes 3 speeds, sometimes variable speed. All right. But because colder air is harder to push through the ductwork, we're going to want to increase the airflow when we're running in the air conditioning system. So as you're checking your airflow, and this is a lot of problems you're going to run into, even with new construction homes, people end up undersizing ductwork. It may be correct in the math, but it just doesn't work. All right. So when you're going around and you got the air conditioning running, try to hit every single room and make sure you got a decent airflow coming out of there. Some people, and Mark, if you're still here, I know you're going to know this answer, but some people use a wind or an airflow monitoring device, and I'm drawing a blank on what that's called right now, but they put that over the ductwork, and I kind of like that idea because now we have kind of a definitive number. And then if we have one room that's significantly less than the rest of them, that could actually be an area where we're going to have trouble heating or cooling. There's also dampers in the ductwork that we can adjust. A lot of people don't realize that in the summer months, we want most of that airflow going to the second floor and then letting that cool air drop down to change and work the thermostat. And then vice versa in the winter months. We want the hot air that we're blowing in the house, we want that to be on the lower floors because that's naturally going to rise up. All right. What I want you to remember off of this slide is that colder air is harder to push through ductwork, so I need more fan power to get the air going to the places that I want it to go to. A coil looked like the letter A, typical slab coil. We find these a lot on horizontal installs. Just one piece. So the A coil had 2 pieces, whereas slab coil has 1 piece. Anemometer. I knew you'd know, and thank you for sticking around. So just to go ahead and give Mark the credit he deserves. You know, he gave us the answer, and anemometer it is. Thank you very much. All right, so now we're back at our evaporator coil. We're going to talk a little bit about how we do our inspection. Let's get some of this text up here. And then there we go. So as we look at our furnace, we know what the temperature is via the thermostat coming into the house. If you want to put a dial thermometer on that just so you can take a picture of it ahead of time and put that in your report, there's nothing wrong with that at all. All right. I want you to remember that 15 to 20 degree temperature drop. So if it comes in at 70, it should be leaving somewhere around 55 to 60 degrees, 15 to 20 degrees difference. If you can see the coil, you know, we're going to be looking for damaged fins, bent fins, damaged tubing. You're going to look for brown or black stains. Sometimes they'll look like efflorescent stains as well on there. Those are going to be showing refrigerant leaks in the past. Sometimes people know, sellers know that they have a refrigerant leak in their home. And I had this happen to me a couple times. They know we're coming there. They know we're going to inspect it. They go ahead and have it charged up because they knew it leaked out on them. We go ahead and run our test. Everything's fine. My client moves in. The system leaked again. And now they need to hire somebody to get that leak fixed and recharge the system. All right. We just did a little remodeling down here at our house, and one of our contractors decided to use our refrigerant suction line to hold the drywall in, so he drove a screw right through it. It didn't make me happy when he did that, obviously. He came and ran. He said he hears gas leaking. He didn't know what it was. It was my refrigerant leaking out of my system. That ended up costing about $750. Not only that, we had to remove the drywall, fix the leak. They had to check and make sure that the leak was fixed, and then they had to put the refrigerant in there. Now, this was on a Puron system, not on a Freon system, but that's still a lot of money. And this was actually a friend of mine who did this, so that was a discount. It would probably be a little bit more than that. So finding leaks in air conditioning systems, I mean, this case I knew right where it was because we had a screw that was driven right into it, so we were able to see it and fix it. But if there's a leak anywhere else in the system, finding these things is not always the easiest thing to do, especially if the line sets or the coils, you don't have access to everything. Now, they do sell refrigerant leak detector kits out there, so if that's something you want to add to your repertoire, you can. We don't do that, but it is an option, all right? So going back to our list up here, if we're looking at the underside, we should see condensation flowing from it. There shouldn't be any dirt or buildup or crud on it, but you're really going to have difficulty seeing the underside of that air conditioning coil. Temperature drop is probably going to be our best test that we could do. Now, don't get me wrong. If we're 21 degrees, that doesn't mean, danger, Will Robinson, But if we're like 25 degrees, that's a pretty big drop, way over the line. And then I would start pushing it off to an air HVAC professional. The coil should be uniformly wet with condensation, and you're only going to see that on the underside. You're not going to see that on the top side. Definitely there's not going to be any ice buildup. If we see ice anywhere, whether it's, on the refrigerant lines, on the coil itself, we're low on refrigerant, all right? So ice buildup is the number one indicator is going to be for low refrigerant. So we know we're going to be getting condensation coming from this coil. We have to collect that condensation, and we have to drain it to a floor drain or put a pump, someplace where it's going to go to a safe location. All right. I don't really get too much into these things. If they're going to put it into the soil stack, as it shows in the upper left, you need a trap of some sort there. We don't want to take a chance for letting that sewer gas come back into the house, and then now we're circulating it through our fans. It's just not a good idea. Most people, they're going to go ahead and put it into the floor drain. I have heard of one test or one question, and in fact, I think we put it on ours as well, where, when they start asking these questions, you got to kind of go back to the old Sesame Street stuff when we were kids. And when they said one of these things is not like the other, and talk about that. So if you see answers where the discharge tube should discharge above a sink, above a tub, in a floor drain, above a floor drain, or which one should it not? Above is fine. We want to have air gaps, but in is going to be the wrong answer. And we don't want to take a chance of getting any bad gases or any bad water going ahead and clogging these things. Now, the truth in life, everybody puts a little elbow in there, and then they put that into the floor drain. The problem is if you just leave it on top of the floor drain, somebody's going to come in there and kick it, and then water's going to be all over the floor. So as long as it's not in the water, I guess everything's fine. But, yeah, that's not something I go overboard with. All right. Now, if we're on the first floor or an attic install, we need to have a secondary means to protect any sort of overflows or clogs that come into play. So if we're in an attic or anything other than a basement concrete floor, let's put it that way. So if I got structure underneath us, we need to have some sort of a protection. Even with a crawl space, you have to do that too. All right. So here they're showing that we put a pan underneath it. We're going to have our primary drain, and this one they're taking into the plumbing stack. Because it's going into the plumbing stack, it's trapped, all right? And then the waters, and that'll keep the sewer gases from coming into the house. But if that primary drain gets clogged, and now water's not draining there, it's going to start leaking on the floor. That's where the secondary pan comes into play. Now you'll see a few different solutions to these. Some will have alarms in them. Some will have cutoff switches. So there's little floats, so if it fills up with water, then the air conditioning system is going to shut down. Other ones are going to have another drain, but typically that drain is going to go someplace where it's noticeable. So you'll see the pipe out there. The pipe will always be out there. You should never see any water flowing from it. But if someday you go out there and you see that it's dripping out of there, that's telling me you got a problem. All right, our primary drain is clogged and water's flowing out of the secondary drain. Somebody needs to get up there and make sure that the primary drain is freed up and go ahead and drain the water as it should. All right. Now, normal flow of air, we're never going to put our air conditioning coil before our gas forced air heat exchanger. All right, that just doesn't happen. In this drawing, they're showing this as an electric furnace. All right, so you can see the electric coils on the right side, then the blower fan, and then we have our slab coil before that. So the air is flowing from left to right. Because the air conditioning coil is going to be under a negative pressure, that also has to have a trap in it. If I don't have that trap, if I don't have something that's going to stop that water from going backwards, so the air is going to be coming back in there, then the water is going to have trouble getting into it just to drain in the first spot. The air is going to keep it backing up into the pan. But once I got that trap in there, then the water is going to flow and it'll just get past it just fine. It won't be an issue. I do want to stress, though, when we're dealing with gas forced air furnaces, which is what we mostly have in our area, the air conditioning coil goes after the heat exchanger and not before. In this drawing, we're showing before, but that's mostly because it's a electric furnace that comes across. All right. And this is doing the same thing. So here they have the air filter, then they have the air conditioning coil, blower fan, and then the electric heating elements. This is very common when we're talking about electric furnaces, and again, that has to be trapped. All right. Sometimes we don't have a floor drain near us, and if that's the case, we have to put a condensate pump in there. It's going to be difficult. Sometimes you could stick your finger in there and trip the pump to see if it works. But in all reality, if the air conditioner has been running and you're in the summertime, you'd have water all over the floor if it wasn't running. So that's going to be our number one clue. But again, this is what with the forced air furnaces, what's not shown in this drawing is the actual filter. So the filter would be before the fan. So the airflow always goes filter, fan, heat exchanger, then our air conditioning coils. When it leaks, it's going to leak on top of the air conditioning, on top of the heat exchanger. It's also going to be leaking on top of the blower fan. It's going to be on the floor of the furnace as well. All these items are going to damage our furnace, so keeping that primary drain clean is important. I can't stress it enough. All right. Watch for the coil if somebody does install this upstream of the heat exchanger. Now we're going to be adding moisture and humidity onto the heat exchanger. That is going to be creating a problem. We just can't do it. All right. So again, it's filter, fan, heat exchanger, air conditioning coil. In this diagram, we're showing air conditioning coil, then the blower fan and the heat exchanger, and that just would be wrong. I made mention before on scroll compressors, and they need lubrication, and the lubrication is inside the refrigerant, and so that just constantly moves through the whole system. As it's a gas or a liquid, it's basically a lubricant as well. All right. So sometimes you can buy an air conditioning system that's already pre-charged, and I shouldn't say sometimes, they sell them today. So there's a lot of people who will purchase the indoor coil fully charged with refrigerant. They'll purchase the line set that's fully charged with refrigerant, and then also the outdoor cabinet coil that's fully charged with refrigerant. And all they do is hook up these three things together, kind of like hooking up your propane tank to your gas grill. And once they're all connected, then the whole system becomes one system again. And the refrigerant's already there. But when you do it that way, you can't cut the refrigerant lines. So you're going to have to buy a line set that's longer than what you actually need that comes in there. So there's always going to be extra line set when it comes to it. So what we don't want to do is have those coils that's showing on this screen. We don't want to have those going up and down. We want them sideways as they're showing on here. If they're up and down, then the lubricant is going to be getting caught at the bottom of these, and it's not going to properly lubricate our motor. So again, it's an easy fix. Turn them horizontally. Don't leave them up and down. I like you to know about the sight glass and the filter dryer. These are always going to be on our liquid lines. So we can look at our line set in the little picture there. You can see the skinny line with no insulation on it, and then you see a thicker line with the insulation on it. This particular one is near the indoor coil, and then the liquid refrigerant is actually flowing towards the coil. And I take that back. This is usually going to be on the outdoor coil, so I was mistaken on that. And that's where this picture is. This is on the outdoor coil, so the refrigerant is flowing from left to right on here, and that's where that arrow is pointing. If I popped off that sight glass, that little plastic cap that's on there, when this air conditioning system starts up, I'll probably see a whole bunch of bubbles flying by there, all right, as it goes through. And then as the temperatures, or I should say the pressures, get up to the proper pressure, so my air compressor builds up enough steam, all those bubbles are going to disappear, and it's going to be clear liquid that goes through it. All right. So it could be near the condenser. It can be near the expansion device. It doesn't matter. We just need to make sure that the refrigerant's flowing the right way. That arrow on there is going to signify which way it does flow. The liquid refrigerant should be flowing towards the indoor coil. All right. They're usually installed on either larger systems, or if somebody cut the refrigerant line sets and they solder things together. If somebody's afraid that any of that solder or debris of any type is inside that line set, then they're going to go ahead and install the filter dryer on there. The whole idea is we don't want to let any of that debris get either lodged into the capillary tubes, into a TXV valve, or even worse, our compressor, if it damages those scrolls in any which way. All right. It contains a cotton filter and a silicone, as well as a drying agent, but again, it's all going to be liquid that runs through there anyway. Watch for frost accumulation downstream of this. Again, it means a partially clogged filter or loss of refrigerant. If bubbling is present, and I would say give it 3 to 5 minutes. All right. So if bubbling is present on this system, that means we got air that's getting through the heat exchanger. We got air that's getting through the condensing cabinet, and everything should condense to a liquid. So I should not have air going through there. In the beginning, it's okay, but after about 3 to 5 minutes, it's not okay. And it should be clear, and you shouldn't be able to even tell that anything is moving through it. So if you get a chance, if you run across one, you don't have to tell anyone why you're doing this, but just ask somebody else to go inside, turn the air conditioning on, lower the temperature, so it kicks on, and watch that sight glass. And you'll see the bubbles go by, and then you'll see them start to reduce the amount of bubbles, and then eventually all the bubbles will be gone. And again, that tells us everything's working just fine. All right. The evaporator fan, we don't really have a separate air handling unit. Now, you may run into just an air conditioning system with just an air handling unit. You'll see that a lot with space packs, or if somebody has steam heat or hydronic heat and they still want to go ahead and put a central air conditioning system in, they're going to have to run separate ductwork just for that. All right. In which case, I think you're always better off putting a furnace in. That's just my 2 cents. Just because if something goes down with the steam heat or the hydronic heat, at least you got another backup system that comes in there. Not only that, but you can circulate air and filter that air out as well. You can't always do that with steam and with hydronic. You can also add a humidifier on these things. There's a lot of other bonuses that you could put to it to go ahead and make your home more comfortable. All right. But typically on this slide, what I want you to understand is that we're going to use the blower fan for the furnace is going to be the evaporator fan, or what circulates the air through the house. All right. Older fans, they're going to have a belt drive on them. I would encourage, well, first of all, if you run into a furnace that's that old with not a direct drive and it's a belt drive unit, you better be preparing your clients that they're going to be needing a new furnace or a new air handling unit. It may run forever, but I just kind of want to plant the seed and put the thought in their head. I would also encourage them to get an extra belt of the right size and have it just sit right down there on the floor inside that cabinet in case it's needed. Belts do break. It's just a matter of time. So there should be a little bit of play on it. They're talking about 1/2 of an inch to 1 inch on there, but it shouldn't be drastic when we come to, the movement and the play on it. Look for cracks. Look for frayed sections. Anything that says that this thing's getting to the end of its life. All right. And Murphy's Law always prevails. All right. So that belt will break at 2 o'clock in the morning on 100-degree heat, and you're not going to have any air conditioning, and you're not going to be able to call somebody out till the next day. All right. So sometimes being able to fix these things on your own isn't a bad thing. Ductwork adequacy. This is not something that we normally inspect for, so I don't put any sort of measurements. I would like you to know the rule of thumb. The returns should be at least equal to whatever the supplies are. All right. Now, a good clue when something's not working right is when the furnace is running or the air conditioner is running. If I'm creating such a negative pressure inside my ductwork, those bigger ducts will actually lift up. Discussion of ductless AC today. No. So Mark just asked me a question if there's going to be any type of ductless air conditioning. I got nothing on that. So the answer is going to be no, nothing's in there at all. Sorry. Going back to the ductwork. So if the ductwork starts collapsing and going up, so I don't know if you've ever heard when the furnace shuts off, all of a sudden you hear this big whomp in the ductwork as all that pressure is releases. That's a pretty strong indicator that it's not the right size. Now, it's still hard to justify, tell someone, well, you're going to have to tear all the ductwork out and put bigger ductwork in. All right. I think I would rather, before I say anything about that, let people know what's going to happen, in their home. But I would still go to every room and make sure I have a decent airflow coming out of that. And that would take a higher priority for me than anything else. Larger ducts required for air conditioning systems. We kind of talked about that earlier. There's always a plan B. So if I have a stronger fan, I can go ahead and get that airflow through it as well. So when we check our ductwork, we like to check it for both air conditioning and for heat at the same time. Vapor barriers, air conditioning ductwork. This is a test question. If it's running through an unconditioned area, and we're talking about ductwork running through an unconditioned area, then it does have to be insulated, and it does have to be insulated at a minimum of an R4. That would be a good number to remember. Any breaks that we have in the ductwork is going to end up being heat loss. So there's a product called aero sealing right now that actually is, a lot of people are really high on it. And this is something too, if you want to get into energy efficiency in the homes, this does fall under our realm. So people do blower door testing, ductwork testing, and you can actually put pans and check pressures and see how much leakage is coming from these items. I think it's a fantastic opportunity if somebody's curious on it, and there's nothing wrong with adding this to your repertoire. I got one friend, Joe. He's a home inspector, Insight. I think it's Insight Inspections. I know he's in the western suburbs, but he does a lot of blower door testing, a lot of duct testing, and a lot of this has to be done for new construction before people are allowed to get their occupancy permit as well. So just a thought and idea. Testing cold air returns. There should be enough pressure to pull the tissue towards the grill, so we should have a decent airflow. And simple toilet paper or a nap or a tissue paper or a Kleenex. Just put that on the interior or the return grill, and we should have enough airflow. Sometimes you'll see a central return that's on there. When that happens, air is going to be flowing through the doors, so we kind of have to check that with the doors shut as well. All right. Typically, we're going to want, if they're going to use the door in the bottom of the door, we should have about 3/4 of an inch on the underside. Me personally, I like it when they put those vents up over the door, or at least on the side of it, so they let the air flow through that way. I know that doesn't help much with sound, mind you, but if you don't let the air out of the room, then we can't let more air into the room. Sometimes you'll have that 3/4 inch gap under the door, but then the people moving in there are going to end up putting carpeting down. So that carpeting is going to close off that gap on there, and if they do that, then that obviously defeats the purpose. So a little trick that I do when the furnace or the air conditioner is running and I have a central system in there, I'm going to close the door and I'm going to close it slowly. And if the airflow around the door is strong enough, or I should say the opening is small enough, then that airflow is going to pull that door shut. And as it pulls the door shut, I know I have to either put a vent or increase under the door. All right. Slugging, I'd like you to know that term. I brought this up before where we have to only send a gas through a compressor. All right. So when we're dealing with the compressors for the refrigerant, if we put a liquid through there, we could damage it. And I've only heard this once. And I don't want to, mention whose house it was, but I only saw this while I was a fireman. It was in the wintertime. The neighbors called complaining that the house was making this loud bang, 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 bang noise. And when we arrived, it was really loud, remarkably loud. And it was I think he was like a rapper or something like that, and he couldn't leave Cook County. So I ended up working for the village of Northbrook as a fireman there, and I retired a few years ago. And when we got called to this rapper's house that he was renting over there, we pull up and we just hear it from the front as soon as we pull up. We walk around to the air conditioning unit, and this thing was slugging. So all the refrigerant was a liquid, and it was like a machine gun going off. It was that loud. So the only thing I did was pull the disconnect to the air conditioner outside, and once that happened, then everything was good. So, and we're going to talk about TXV in a little bit. BJ just asked a question. And I'll throw this up on the screen, about thermal expansions. So TXVs or thermal expansion valves, we'll bring those up what they look like in a little bit. All right. Well, I guess we're going to bring it up now. All right. So I apologize for that. So when we're dealing with thermal expansion valves or TXVs, these end up going on the liquid line, and that's where we'll see them. And then there's going to be another tube that goes to the suction line. So if somebody does put a mismatch system in and they want to be able to make it work, they can go ahead and make this work. All right. And what this does is when the suction line gets low enough, then that TXV is going to open up and let more liquid get into the indoor coil. And then once that pressure starts building up too high, the TXV is going to close until finally it gets to that happy medium where it stays open just enough to let the right amount of refrigerant come in there, and we get our equilibrium of our system. So that as we're adding pressure from the air compressor, we're releasing the same amount of pressure from the TXV. I would like you to know the term TXV. I want you to know the term stands for thermal expansion valve. I realize this is a diagram. I realize this is a diagram on there, but that's basically what they look like. A little flying saucer type thing on the top, and then you'll see it located on the liquid line coming out of both ends. Let me see here. All right. One thing you guys might want to mention to your clients is ductwork thermal expansion, which can make a variety of sounds, one being sound dripping water, falsely indicating a leak. Now, I have heard of this as well. I didn't know that was the name of it, but I believe what BJ's sharing with us, and a little bit of a thing about BJ, really smart guy, worked for a builder for a long time, and so obviously they would get a complaint from somebody who moves in there, something that's going on with the house that they don't really understand. So he has to figure out, is this a problem, get the problem fixed, and so forth. All right. But in this case, yeah, you hear that dripping. And so what's happening is the ductwork is getting warmer, it's going to expand. As the ductwork gets colder, it's going to shrink. I'm sorry, BJ, I didn't understand what you were mentioning to me when you said thermal expansion before. As that's shrinking and expanding, there's pieces that are going to slide in between each other. And it's just going to be a little bit of movements as it comes through it. So sometimes it sounds like dripping water that happens in there. And that can also happen in plumbing systems too. So you'll find, or waistline systems more specifically, especially with like cast irons. If you're running hot water coming through there, sometimes you're going to hear the thermal expansion of the steel when it comes to that. Great point, BJ. Thanks for adding it in there. All right. All right. Lifespans in our area, and if somebody disagrees with me, you're good with that. But we usually tell our clients they'll get it roughly about 20 years out of an air conditioning system. Sometimes we'll say 15 to 20 years. So it depends on how much it's using it, how many heat loss days or heat gain days there are, is how long the air conditioner is going to actually be running. So down in Florida, Texas, Arizona, where the temperatures are a lot hotter and everybody's using these things more, obviously they're going to have a shorter lifespan. You tell one of the home inspectors down there that we're going to get 15 to 20 years out of an air conditioner, they usually tend to laugh at me, all right? But that's because they're used to replacing these things every 5 to 10 years when it comes to it. So the cooler climates, they last longer. The warmer climates or warmer areas, they're slower. Now the test, if you haven't taken it already, is the National Home Inspector's Exam. So because of which they're going to be asking questions about different systems located throughout our country, all right? One of the items people use for air conditioning is something called an evaporative cooler. Now it has a nickname of a swap cooler as well, and it works on the principle of, again, changing state. You know, so instead of using refrigerant going from a liquid to a gas to absorb heat, it actually uses water, and it uses it on the principle of if I add humidity to a building, and that moisture lands on people, it lands on objects. And if I do that in an extremely dry climate, so like Colorado, Arizona, New Mexico, all right, Nevada, desert, areas in the desert where climate is very dry, where it comes with it. Just because it's dry, that liquid is going to want to evaporate quickly. So if I put it in a fine mist spray, and it lands on objects and it's dry outside, it's going to change to a gas or evaporate quickly. And the same rules of science still apply. If I'm going from a liquid to a gas, I have to absorb BTUs. So as I blow moisture into a room and something gets wet, then that moisture is going to basically, as it changes to a gas, it's going to absorb the heat of the items that it's touching. Those items will be cool, and then the rest of the house is actually going to be cool. So it's hard for us, northerners, to understand this, but in this case, with these evaporative coolers, they run with high flow air, big ductwork. You actually keep your windows open when you're doing this. You blow the humidity in the house. That moisture that's going into the house evaporates because of the very dry climate that they live in. And as it evaporates, it absorbs the heat of all the objects in the house, including the human beings that it touches. And they actually work fantastic. You know, everybody that has them says that they're marvelous, all right? We can't use them here in the Chicagoland area because our summers are very humid. And if we add more humidity to the air, we're just going to be even more uncomfortable, all right? So we don't do it here. Other areas have problems with it. I mentioned Colorado earlier. They have such long, cold winters there, and the freezing temperatures would also create a problem. These are usually installed up on the roofs of homes, and this is actually what one looks like up there. So the moisture is going to go into that fan. Air is going to come from the outside and then blow it throughout the house. So they're big units that we end up seeing. Now, I was actually in Albuquerque, New Mexico. I believe when we took this picture, we were on a hot air balloon ride because that was on my bucket list and I wanted to do it. And when I saw this, I was like a kid 2 days before Christmas. I'm like, oh my God, that's an evaporated cooler. I never saw one. So I literally made the balloon pilot come down to the roof. And you could see we almost landed on his roof. We were right next to his house. And then he went back up again. I felt like a knucklehead doing it, but it was awesome. So large amounts of air. The windows are open. Blow humidity in the house. The humidity lands on the object. Dry climate causes it to change to a gas. When it changes to a gas, it absorbs the BTUs, and this actually works very well. All right. System operates on principally on water outside air. We just said that. The moisture feels cool on contact with the skin because it's evaporating. It's only used in very low humidity. Water is added by a moist pad, water dripping. Same type of humidifiers that we use in our own houses, and then more of a nickname than anything else. They call them swamp coolers. You'll hear that as well. So we're going to go, the next step is we have an understanding of an air conditioning system and how the air conditioning system works. And in short, again, our compressor compresses the air, takes it to the outdoor coil, high temperature, high pressure. It's a gas. It goes through all those coils. It's expelling the BTUs. As it's expelling the BTUs, it wants to convert back to a liquid. Loses some temperature, loses the liquid, still remains a high pressure, however, until I get to the metering device where the pressure now drops. Now I go into the indoor coil, liquid, low pressure, low temperature, absorb the heat from inside the house, cause a refrigerant to start boiling, and that boiling converts it from a liquid to a gas. I'm absorbing BTUs from inside the house. In other words, I'm removing heat from inside the house. And now I'm going to have a gaseous state. It's still going to be under low pressure. It'll be warmed up until I get to the air compressor. But what if I did this a little bit differently? All right. What if I took that evaporator coil that's inside the house right now where I'm absorbing heat, and I put that evaporator coil outside. And then I put the coil where I'm discharging heat, and I put that inside. We can do that. In fact, we could take this air conditioning system and we could basically reverse the flow of the refrigerant. So instead of going one direction, we make it go the other direction. So now, if we start at our compressor again, we're going to compress our gas. It's going to remain a gas. And then that one device there is the only thing we added. It's called a reversing valve. And that reversing valve is going to be where we send our refrigerant, so it goes to a different direction. In this case, we come out of the compressor, and now we're going high temperature, high pressure, gas, and we're going to send that to the indoor coil. All right. So now I'm going to have hot gas refrigerant going to the indoor coil, and since it's going to be cooler inside, I'm actually going to be discharging my heat on the inside. So as I'm discharging my heat, now what used to be my evaporator coil, it used to go from a liquid to a gas. Now it's going from a gas to a liquid. So it comes out of there as a liquid, hits my restricting valves, my capillary tubes, a reverse TXV, whatever. All right. It's going to lower the pressure. It's going to remain a liquid. And as we lower the pressure, we lower the temperature. And now that cold liquid goes outside, colder than what it is outside. Now, even if it's 40 degrees or 50 degrees, if my refrigerant's 20, then I'm still warmer outside. I could have still absorb heat into my refrigerant on the outside. Cause it to boil, so now my outdoor coil, which used to be my condensing cabinet, is now my evaporator cabinet, because now I'm causing it to boil, change back to a gas, gas comes to the compressor, and so forth. So a heat pump, or I should say an air conditioning system, is technically a heat pump, all right? But when we use those terms, the difference between a heat pump and an air conditioning system is that reversing valve. In this diagram, you see it on the bottom there, and that changes the direction. So right now, this is in winter mode. So right now, we're absorbing heat from the outside, and we're bringing the heat to the inside of the house. I do want you to take note of the temperature rises, all right? And if anybody's ever dealt with a heat pump before, it's pretty difficult to say, is this thing actually working, you know? It's only a 10 to 15 degree temperature rise. So if I'm 70 degrees in the house, that means the air flowing out of there is going to be between 80 and 85 degrees. So if I look at my ductwork, the air that's going to be coming out of my ductwork is going to be about 80 to 85 degrees, all right? As that's happening, I put my hand on it and I feel it. Well, my body temperature is 98.6 degrees. So if I'm 98 and that airflow is 80, that's actually going to feel cool to the touch as the air that's coming over me. So I'm going to feel like I got cold air that's blowing out of the ductwork, when in fact it's actually heating my house, all right? So it's a little bit awkward when you see these things run. And we don't want to put heat pumps on, what do you call those, setback thermostats where we change the temperature a lot, you know, like a Nest where, you know, we'll lower the temperature or let it heat up in the house when we're at work, and then all of a sudden about a half hour before we come home, we turn it on and expect everything to drop. It doesn't work well that way. Heat pumps, when they're working for heat, we want it to stay consistent. All right, we want them to be on and maintain a steady temperature. That's when they work best. Thermostats for heat pumps, and I'll show a diagram on this, they usually have two thermostats in them. One is going to be for the heat pump, but if the heat pump can't keep up with it, so I'm just losing too much heat, then there's going to be, they either call it emergency heat or auxiliary heat. There's going to be some sort of backup heat plan that comes in there. So when we look at it, we build it up, and now we're putting it into air conditioning mode. We started our compressor again, high temperature, high pressure gas. We aim this to our outdoor coil, where we're going to be still a gas, high temperature, high pressure. We're going to blow the outside air over this. We're going to discharge our heat outside at this point in time. It's going to change to a liquid. It's going to go to our metering device. As it comes to our metering device, and I should say, I did say, we changed to a liquid. So the liquid's going to hit our metering device, where we're going to lower that temperature. When we lower the we're going to lower the pressure. When we lower the pressure, we automatically lower the temperature, but we still remain a liquid. That liquid comes to our indoor coil. where we're going to be absorbing heat. At that point in time, it changes state, where in the change of state, it's going to leave as a gas, where it's going to go to the compressor and get pressurized again. And when it pressurizes, it goes ahead and increases that temperature again. And again, the only thing that's changed on here is that reversing valve and where it sends that high temperature, high pressure gas. If we send it to the inside, we're going to discharge heat to the inside. If we send it to the outside, we're going to discharge heat to the outside. And wherever we're discharging our heat, we're absorbing heat from the opposite end. A heat pump works in both directions. Obviously, it can't do that at the same time. It's one or the other. All right. But a heat pump, as it differentiates between an air conditioning system, is strictly because of that reversing valve that exists there. Numbers that I want you to memorize, and these are simple tests that we can do. We talked about an air conditioner. That's going to be a 15 to 20 degree temperature drop. All right. So as we measure the incoming air to the exhaust, 15 to 20 degrees. A heat pump in standard heat pump mode, so the furnace in this situation or whatever additional heat that they have isn't operating, is going to be typically a 10 to 15 degree temperature rise. Air conditioning, 15 to 20 drop. Heat pump, 10 to 15 rise. All right. If that's not enough to heat the house, and we go a little bit further, then the auxiliary heat kicks in. So whether we call it auxiliary heat, emergency heat, I don't really care. All right. It's really the same thing. Sometimes people will make it a furnace. In this diagram, we're showing an electric furnace. So that electric furnace is our auxiliary heat. So instead of the heat pump running now, the auxiliary heat is going to be running. Now that varies depending on the furnace that's installed for this. Typically we could find this temperature rise on, on the furnace itself. Here they're saying it's 40 degrees for the temperature rise. And, I've been finding that varies. I've seen anywhere from 25 to 55. I've seen 50 to 80. All right. So looking at that data plate, I think, is more important than looking at these diagrams and memorizing these numbers. But if you're going to be taking a test, then that 40 degree number should be a pretty decent number to memorize. All right. Geothermals, they kind of work on the same principle as the heat pump. We know that about 5 feet and below, that the average temperature of the Earth is going to be roughly around 50, 55 degrees, somewhere in that ballpark. All right. So instead of having an air conditioning coil where I'm absorbing heat from the air, instead of having that present, I'm actually going to use the heat that's present in the Earth. So most air conditioning systems that we have are what we call air-to-air systems. I absorb heat from the air inside the house, and I discharge heat to the air outside the house. If I want to use it as a heat pump, I'm going to absorb heat from the air outside, and I'm going to discharge heat to the air inside. If I'm doing a geothermal, like what we're seeing in the diagram, I'm going to absorb heat from the earth, and then I'm going to discharge that heat to the air inside the house. And even if I ran it in reverse, I can also discharge heat to the outside as well when it comes out that way, or to the earth as well. So if I'm going air to earth, it's a geothermal. They actually have well air conditionings, and a lot of people refer to those as geothermals as well. So what they'll do is drill a deep hole, and just like they would be drilling a well system, and they would run their refrigerant tubing into that well so that would be absorbing or discharging the heat that's present as well. Those are how geothermals differentiate from anything else. Cooling towers, I don't want to go into these too much. Honestly, it's kind of over my head. So usually high-rise buildings, large commercial buildings, you're going to see cooling towers where they're actually going to be running water over the exterior coils. The idea of the water flowing over it is it's going to be absorbing more of the heat out of the refrigerant when that works with it. They're common. You're going to see them if you get involved with commercial inspections or if you start dealing with condo buildings as well. And with some condo buildings, they're just going to have air handlers in there. So I think we're going to talk about that in a minute. Most common type is the aqua tower. And again, water is used to cool the compressed coolant over the evaporator systems. All right. So just a couple pictures and a few things that we end up seeing here. I like this picture because it shows the tubes that the refrigerant is actually running through. And then it also has the fins on there as well that the air was flowing through. Now this happens when a dog urinates on the air conditioning system. Those fins are very thin and they're fragile. All right. So a dog's urine sometimes is pretty acidic. So if they keep peeing on the air conditioner all the time, then it wears away at the fins. Now it didn't hit the copper tubing, it didn't damage that, but the fins that are on there, that it did damage. All right. So but the tubing itself is where the refrigerant runs, and then those up and down fins, you can see how tightly spaced they are together. So we get a lot of airspace that's touching the metal that's on there when it runs through. We do have to keep those clean. Speaking of which, I'm looking outside my office window right now, and yeah, I got a pretty thick cake of dirt on my outside fins, so I got to get those hosed off and cleaned up. But don't tell anyone, please, especially the lovely bride. All right. So I did go about 2 hours. I hope this was helpful. I'm more than happy to talk about any questions if anybody has anything that they want to put up here. And I'm not trying to escape. I know it takes a few minutes to type, so I will sit back and hang tight for a little bit. I am going to start up again at 1 o'clock, and then I'm going to continue the plumbing section on this one. It goes a little bit quicker when we don't have a lot of questions on there, and I know in this type of environment it's not always an easy way to do things. But nonetheless, I do hope that this was helpful for you guys. I hope it gives you a better understanding. It is going to stay up there on that YouTube channel, so if you do want to listen to it again, feel free. But as far as I'm concerned, I think it's kind of important that we understand how air conditioning systems work and some of the problems that we run into these things. All right. So I'm going to take myself off the screen. I'm still here, but I just don't want to look blatantly dumb in the picture. But I'm just going to sit tight here until basically everybody's signed off. Gotcha. That's a nice thing to add. So Mark jumped on there. He said he thinks the ductwork works like a heat pump. They just use heat exchangers and every place that you want to have heat and cold. And I have seen these things that are smaller units that are up over the door, and they're basically per room. I think you're 100% right. And I don't know if they all use the same air compressor on there or if each one has its own. Like I said, I don't see too many of them in my area, and I'm not afraid to say I'm ignorant on the subject. All right, guys, without anything popping up here, I'm actually going to stop this. And thank you. And again, I hope this helps. All right. If you guys come back, and I hope you do, I'm going to start up again around 1 o'clock. Thank you.